Okay, well, we have 11 presentations. That's perfect. We have, what, 3 hours. Lunch is going to come around noon, a little later today, so we'll have plenty of time for the presentations, a little discussion after each one. So let's start with Lauren here. Is everything hooked up on the computer, right? Do you think? Okay. So Lauren is going to talk about Hawaii. Single page slideshow. Now, is it still okay? Okay, perfect.
Okay. Hi, I'm Lauren. And yeah, today I'm going to talk about a time series that I made for Kilauea volcano. So okay, yeah, so my name's Lauren Ward. I'm a graduate student at the University of Hawaii. And yeah, I'm a PhD student going into my 3rd year. So actually the PDF, I had like animations, not really, but so the PDF ruined my, so I'm gonna go back.
Oh, you can go back.
Yeah.
You're doing it through Google, is that okay? We have also have.
Oh, I need to download it. I see, yeah. Sorry.
Yeah, there's a folder on the desktop. Yeah. Yeah, the problem is, it comes out really small, but it's bigger on the other screen. You're there.
Yeah, PowerPoint doesn't work for presentation mode. I can't figure out green screen.
Oh, I can't. Okay.
Why don't you start with a PDF or do it that
Yeah,
way?
it's okay. It's not that big of a deal.
When we get to the animated.
Okay, it's not a big deal. I just have some plots on top of each other right now. Is this okay?
Yeah.
Okay, good. Okay, so this was the slide. There's 3 maps of where Hawaii is located that you can't really see anymore. But yeah, so this is Hawaii on the globe. And then the second picture was a image of the chain, all the islands in the Hawaiian chain. So we're looking at the big island of Hawaii, and then Kilauea is like there on the big island. Okay, so why am I looking at this region? Well, it's still an active volcano. The last eruption was in May 2018, and these are images from that eruption that happened last May. And deflation and inflation events are common eruption precursors, and InSAR can capture that motion. And so it's important to regularly monitor the volcano. Okay, so this is my first phase image that I got from doing part of the time series. So this is just a phase interferogram from March 7th to July 8th. And so in my time series, later on, I only used 3 scenes for time purposes. And so there, I also have a SAR image that I grabbed in May. But so this is just a normal interferogram, phase interferogram from March to, July. And then I projected it into line of sight. And so these contours are 25 millimeters. And so right here you have about 75 millimeters of deformation. And since this is a descending track, that would be positive motion is towards the satellite, so that would be motion either up or east. And then right here on Kilauea volcano, this is the summit of Kilauea, you have, let's see, about 50 millimeters of deformation that it sees. But so after I made the interferogram, besides the filtering that's already done in the program, I also just detrended the image to try to help with atmospheric correction that can occur around the summit since it's a very tall structure. Okay, so then this is now the time series result, which gives the cumulative displacement. And if you look at them side by side, you can see that they look similar, but they're not the exact same. And ideally, the time series displacement image is giving a more accurate result because it's considering the scene that occurred in between the two endpoints, right? And so if I had more scenes, then this would be even more refined. But you can already see that in this one, it's a slightly smoother grid, and it actually captured a bit more deformation than just the line of sight. Yeah. And for the cumulative displacement, I also wasn't able to do the atmospheric correction like the presentation yesterday was talking about because I only used 3 scenes, so I needed more to do it. Yeah, so then also the time series will spit out a velocity in millimeters per year based on the deformation that's occurring between your scenes. And so I think the max was like 350 to negative 350 millimeters per year of deformation, which is kind of interesting. And then it also gives you a digital elevation model error, and I think it's in millimeters. Is that what? It's in meters? Oh, okay, sorry. So there is up to about 1 meter of elevation error, mainly around the Kilauea summit. Yeah, probably. But okay, so now to make an actual time series, I cut the grid to just this tiny area around Kilauea, and then I found the average of the grid, and I plotted it as displacement versus time. And yeah, so again, positive displacement is upward towards the satellite. So this is a potential inflation event that's been occurring from March till earlier this month. Yeah. Yeah?
You have your ADU club.
I thought for myself.
So Mauna Loa looked like it was red too. Is that inflating?
No, this is probably air, or not probably, is air. I don't know. But a lot of Mauna Loa is very tall, right? And so, like I said, there's no atmospheric correction. I've only had a detrend of the grid. So all of this stuff over here is most likely errors. Yeah. Yeah. So.
This red,
yeah.
the displacement, do you think that's inflation or is that
It's kind of hard to tell with just InSAR. I think that if you compared it with GPS stations that are stationed around there, if they were showing an east component, then you could say it's most likely east, or you can then quantify what's going. No, east. Is this not right? It's going towards, because positive is motion towards the satellite and it's looking west, so that would mean east or up. Yeah? Oh, if I have the other. Oh, yeah, yeah. If you look at the other look, yeah. Yeah. Okay, yeah. This is unwrapped, yeah. Here? So there's a fault around here that before, I know my advisor is saying that there is possible like slumping event that could be happening towards the ocean. So maybe that's what's going on, maybe not. But yeah, that's a decently big signal here.
I mean, in general, you have a large discontinuity.
Oh, here?
Or just car bar thing, right? For example,
From here to here? At what part? From this area?
It could be just a water problem, but
Is this continuous
Oh,
color?
yeah.
Is it zero? We can't really tell. It looks like
Um,
almost like
Yeah.
Trend the line that crest the model.
Yeah, so this is the edge of Mauna Loa. So yeah, it might be a big jump there because of that. Yeah, I think it's atmosphere.
are you trying to compare it, like maybe GPS sensor or something like that?
Yeah, so ideally in a time series like this, you'd also have GPS plotted, and then you could get a better, it's like in the examples they were showing yesterday, usually you compare it with GPS. And then if I was able to do an atmospheric correction too, then I would see how that changes as well, because I'm assuming it would. But yeah, again, I just use 3 scenes and like a really tiny piece of grid just for, yeah, processing quickly. Yeah.
how do you choose your reference?
My reference point of
Yeah, of the program.
my reference, what do you, sorry, I don't understand the question.
So, I mean, like, normally you choose a reference point which is supposed to have a very stable, like, have no deformation.
Oh, no, is that,
Did you detrend these?
I mean, I detrended it, but otherwise I didn't make any other corrections. This is just like what was spit out of the program. So I don't know if the program does that. Does it choose a reference point when you, no, yeah, so that hasn't been done yet. This is very preliminary.
I should point out that Lauren and Bridget Contour and
Lillian, yeah,
were making interferograms of this in real time
yeah,
while it was happening. So you've had a bunch of tools, but this is your first time.
yeah. So I've made like just single interferograms like every 6 days for
You would rotate.
for a while, for a long time, but I've never done and gone through a full time series before, so that was cool to learn. Yeah.
Great, thanks. What's next? Escape. I only made 2 PDFs, so it's Rodriguez. Oh yeah. Yeah. Oh yeah, I have a PowerPoint, but you can't really show. Try getting, if somebody can figure out this PowerPoint, they get 2 of those coasters. If you can figure out how to do the PowerPoint and project. I'll get 2 coasters.
I'm pretty bad with computers, so.
Oh, and the Google. We have 3 ways of projecting. Does it show up on the remote? Oh, wow.
There you go.
Thank you.
Ooh, but I can't see my notes.
Oh, that's okay.
No, it's not okay. Hmm.
You'll remember.
That's weird. That's like. Okay, well, I'll just.
That's a good idea. That's a great idea. You can put one underneath. There's another shelf. I like the Google. Let's go back. Just put it on top. There you go. Yeah.
Sorry. Okay, so I'm going to be talking. I'm Alba Rodriguez. I'm a first-year PhD student at UC Davis, and I study distributed deformation over the earthquake cycle from normal faults. And today I'll be talking to you about my latest obsession, which is fault-related faulting. And hopefully I can make you obsess about it too, so you can fix all the InSAR problems that I've had trying to quantify from an interferogram. So I'll be presenting the results from that. But I got a little bit carried away with the science of why I care about this. So there's like 10 slides of motivation that hopefully can make you motivated as well. And then only 5 slides with InSAR results, so bear with me. So actually, I had this because I didn't know if my interferograms are going to work. So I have plotted the Brazil example just in case, but we don't need that anymore. So let's talk a little bit about seismogenic versus creeping faults. Seismogenic faults are the, I will give you permission from my laptop right away to do that. David Samuels requesting movie access. Send. Ah, sorry, I thought that would work. So, this is really small, and I apologize to the people that are doing this remotely. Basically, seismogenic faults are the faults we think about all the time. They're the faults that can make earthquakes. They go through periods of quiescence while they load, and then they experience a large stress drop during an earthquake. The tips of these faults change their stress state. They get loaded, they experience a stress drop, and then there's some sort of residual stress that stays there over time. On the other hand, creeping faults are not episodic. They experience continuous loading and continuous slip, even if it's at really small increments that we can't see. So their tips are constantly at a subcritical to critical stress state. And where's my publication mode? Okay. So essentially, I think that faulting is a good way to look at the stress state of these faults, and that can tell us about the physics of the tips of an earthquake, which is essentially what's going to regulate when the next earthquake happens based on the inherited stress on it and when it goes next. So these are fault displacement profiles. We see these co-seismically, but we also see it over the long term. There's structural geologists that have spent their entire career at looking at the shape of these. On the y-axis, you have the cumulative slip, and on the x-axis, you have the distance along the fault. And some people argue these are triangular. Some people think these are elliptical. The main point I want to make here is that they always taper towards the tip to something close to 0. And this gradient in slip and that gradient in stress as well results in folding ahead of the fault tip. So we see this in extractive faults and normal faults. In thrust faults, it's universal. As you taper towards the tip, you generate an area of uplift and an area of subsidence at the tip. If creeping faults and seismogenic faults have different stress states, their shape of folding should be different, and this should be something we're able to quantify. So this folding is made elastically. It can be made coseismically. So if you make a dislocation in a homogeneous isotropic elastic half space following an elliptical taper, you get this folding at the fold tip. These are the distances ahead. So you can see that the wavelength stays constant, but as you move farther away from the fold, the amplitude decreases. And I want you to note that this is extremely vertically exaggerated. The maximum displacement for a 1 meter of slip at the middle of the fold is 3 centimeters. So no wonder this is gonna notice for so long, because to notice this folding, you need really, really high resolution topography.
Where is this profile on that?
Oh, sorry, this is ahead of the tip. So there are little cross sections as
Okay.
you move away. Yeah,
Top to bottom a little bit.
Yeah. yeah, sorry. Should have put that in there. So basically this folding is something we actually observe coseismically. This is differential LiDAR from the Elmire-Cucupa earthquake. First thing I want you to notice is that fold slip decreases somewhat elliptically towards the tip. And then you can notice that the foot wall and the hanging wall are warped as slip decreases. This is in the supplement of the science paper from 2012. But this folding is actually something that's also preserved in the landscape, which is kind of surprising because the strains of the folds are just below the limits of elasticity. So why should something that's elastic deformation during an earthquake be preserved as permanent deformation in the long term? But it's there. So this is a hurricane fault in Utah. And if you draw cross sections from A to A prime, B to B prime, you notice that folding of on the foot wall of the normal fold. Oh, there and there. This is just a 3D LiDAR view. That's cool. I used this for a grant, so that's why I had that there, but it's not really informational. And then if you go to the Needles Fold District, which is another set of normal folds in Utah, draw a cross section in the set of rabbit and horse folds, you also see that the foot wall is warped. I think that to test whether the folding shape of normal folds is different requires a good natural laboratory, and I think the hurricane faults and the Needles Fold District provide exactly that. The hurricane, they're both in the same lithological unit, but the hurricane fault is a seismogenic fault. It goes through earthquakes. It's part of the Basin and Range province, and the Needles Fold District is a set of creeping faults. They've never experienced an earthquake. They're creeping because there's an underlying layer of evaporites that's getting dissolved underneath them. So these are essentially only creeping faults, versus if you were to do this at the San Andreas creeping section, you can't really know that that section has always been creeping. It may have been seismogenic at a point. So it's a good way to isolate the physics of this. So what I wanted to do for this project was try to quantify the growth of that folding at the Needles Fold District, because these faults are continuously propagating as they creep. You should be able to get a continuous signal of fold development if the amplitudes of those folds are large enough to be captured by InSAR, and the time spent by the images is long enough. So the Canyonlands National Park is in Utah in the little white square, and if we zoom into that square, right here, it's a confluence of the Green and the Colorado River, and if we zoom in one more time, here's the Google Earth image of that. These elongated arcuate structures are the normal faults I'm talking about. As the Colorado River cuts into the sandstone unit where they are, into a salt layer that's underneath that sandstone unit, it dissolves the salt flows, and that causes gravitational collapse, which leads to the development of those really beautiful normal faults. So one exciting thing is that LiDAR is coming soon, and LiDAR is a great way to quantify the 3D shape of something. Unfortunately, LiDAR coverage is really small and it's really expensive, so we will only have data for those 40 square kilometers, and the area of deformation is much larger than that. So I think here's where InSAR comes in and can give you something that LiDAR can't. The first thing is that InSAR can give you a rate, because you can look at the information over time, and then it can span a much larger area that the LiDAR has. So actually, someone thought about doing this before, and the results are published in this Fourier et al. 2007 paper. And the conclusion they came to is that while they can localize the locus of deformation within the area, they can't really do much more, and that is because there weren't enough images available. This was done between 1992 and 2002 using ERS 1 and 2 data. But now there's also ALOS and there's Sentinel data. So we can actually explore the idea of getting a time series for this. And we can get a much longer time span that may be able to resolve these really small deformation. The entire area is about 2 millimeters per year of distributed deformation. So that's really, really small. So what I tried to do here was take the 2 longest images I could find to try to resolve displacement for that time. We had to use ALICE because my laptop was not collaborating with Sentinel because of the orbits. And I was also having issues because all of the Sentinel scenes overlap in these areas, so I would have had to merge them. So I decided to go with ALICE to make it the simplest I could. And the longest time span I was able to find were images from 2006 and 2009. So that's what I will be showing next. So these are the inputs I used. I used the configuration file for the ALOS Brazil example, and I just modified it to fit the data I had. So I used the DEM, and this is actually the output of the DEM that GMTSAR gives you. And I really like that because it's in the azimuth and range coordinates. So you can imagine being the satellite flying over this and what that would look like. And I used the ALICE images I talked about, the 2006 and 2009 one, using the same frame, the same path, and both the descending orbits. So here are the results. Here's my amplitude. Looks nice. The correlation doesn't look as nice. You can see that it correlates strongly in the middle. Later, I realized that that's actually the highest elevation data, and I used data area, and I used data from November. And it's not supposed to snow there in November, but it might. And the fact that it correlates with the highest elevation areas is really suspicious. And here's my phase difference and phase filter. And the Needles Fault district is somewhere in the middle. So down the line, I think I need to really choose a much smaller area and look at the atmosphere, what's going on. Am I getting a lot of atmospheric noise? How can I filter that out? I should work on a time series to see if that can help clear that noise. And I also need to get better at InSAR. So that's it. So questions? How far away they're? I don't know. Okay.
So you have two, and it's going to take a lot of images to resolve 2 millimeters here.
Yeah, yeah.
And with ALOS 1, there might be 20 images or so, spanning that whole 6 years, which is good. But as Eric noted, the baseline control on that satellite wasn't very good.
Okay.
And so when you get time, make a plot of, if you make a plot of like perpendicular baseline versus time with, and this is 0, and this might be like 4 kilometers, it's huge. And it would go through these cycles like this, and then they would reset it, and then it would go like that. And so you may have made an interferogram between this one and say that one. The baseline could be really long, and so that's why it's decorrelated. So with Sentinel, you don't have to worry about anything. But the good news about ALOS is that you had some pretty good coherence over those many years. So you might want to do both. When you get, you just need a little bit more powerful computer.
Yep.
You can do all the Sentinel. 2 millimeters is a challenge.
Yeah.
What was the spacing of the faults about?
They're spaced about 500 meters away from each other, and it's a little denser in some areas. One of the things I want to do with the LiDAR once it comes out is there's orthophotography for these areas from the 90s. So I could differentiate that. It's going to take downsampling the LiDAR by a factor of 5 to match that, but it will give me some rough idea of the overall change. And there's no atmospheric noise in there.
Yeah. So if you're willing, you could probably see the 2 millimeters. I don't know, 2 millimeters over that short distance. With a lot of sense, like all of them.
It is very, very gradual. It should be constant and really, really small. So I think I'm gonna need a long time
So maybe each fault will have a little bit of creep, is that the idea? And there's 3 millimeters of the whole set.
Yeah, distributed throughout the entire array, which is about 50 kilometers
Yeah.
wide.
That's gonna be hard to see. The
The LiDAR is going to be sub-meter resolution. It's just that the pre-existing data is not good enough. Yeah. When I differentiate the LiDAR with the orthophotography, it's going to be almost 20 years. So you would hope with that you get to the centimeter, but I don't know yet. I'm waiting for the LiDAR to come out. They're supposed to fly this summer, but I think it got delayed because they're flying Ridgecrest this week.
Is that your LiDAR project?
Yeah, I requested it.
So you can write, I know students can write proposals to get.
Yeah, it's the
NCOM
NCOM-C proposal. Yeah, so write that. If you want LiDAR data for an area, write an NCOM-C proposal. They come out in November.
I think you can self-estimate to GPS.
That is one of the limitations. So actually the 2007 paper tried to look at GPS, and back then there was not a dense, if not at all, GPS network, because this is an area that's not tectonically active. So there's not as much motivation to put GPS. So I could deploy that. Okay.
I just need to. Right?
Okay.
I have a question is, for a GMT. So she did mention there's a ILOS 1 data maybe and a cynical data. Is a GMTSAR is able, like the time series, able to mix constellations? You know, at different levels.
And they don't overlap in time. All right.
Escape. There's oh, Michelle.
Can you download that? Is that
Sure.
there's
Google.
another version?
Go to Google. We could take a couple minutes breaks and I'll download and make it into a PDF. Oh, you forgot your.
Oh yeah, my partner.
There's more over there too if you want. Oh yeah. Sure. Okay, quick break. Let's go to Google. Yeah?
Next time offer autographs.
Autographs coaster. That's the way to do it. By the GMT developers. Do you guys want autographs from coasters? So we're ready? So we're ready?
GMT stars. Stars. Not stars.
How do I get to file, new window, Google Drive, and then my drive, plus 19, invitations, and
So yeah, you too.
this one here.
Yeah.
I'll download that right here. Open in Finder. Is PDF okay?
Yeah.
Okay, because then you get the full screen.
Yeah.
Or you could do it in Google. We could have done it in Google Drive.
No, PDF is fine.
Okay.
I mean, you'll convert it anyways at some point.
Yeah. Yeah. Oh no, cancel. Save as. PowerPoint PDF. Put that in there. Desktop. Export. There we go. right here. Nice. View slideshow. There we go.
It really was an accident. So good morning, I'm Marshall Higgins. I'm a PhD student, coming up my third year, going into my foot. What's going on here?
Oh, it's playing by itself.
That's not what we want. We want where's F Max. Full screen. That's all I need. Yeah. Working at Penn State with Peter LaFemina. I primarily do in geodesy, mostly GPS, not InSAR, because InSAR is, as Dejong says, it's lucky. You know, yeah, there's just too much of a random aspect for it. But yeah, so I chose to, this is one of the regions of study for my project, which is studying the CAF, Central American Four Arc Sliver. So this is a actual sliver that's tectonically escaping to the northwest because of the indentation of the Cocos Ridge. And these are some GPS velocities that's showing what's going on. And there's a volcano arc that dots the edge of that sliver. And there's a volcano like every 20 kilometers or so going along this four arc. Okay, so I am primarily interested in Nicaragua. Nicaragua is interesting. Well, this is our GPS network that Pete operates with INITA, the local USGS equivalent agency. And we not only monitor tectonics, but we do volcano monitoring. And Pete's primarily a volcanologist. I am not. I deal with tectonics and fault slip rates. And what I'm trying to figure out is there's something very unique about the CAFA, well, we call it the CAFA for short, in that there are strike slip faults that accommodate this right lateral motion in Costa Rica and El Salvador and going up into Guatemala, but not too far up because it gets really complicated. But in Nicaragua, there's no strike slip fault accommodating the motion. We know why, but we'd like to show it geodetically how it's being accommodated. So that's future work for me. So I decided that I would use InSAR. No, I didn't. I thought that I would try and give it a shot. I knew it would be completely decorrelated because it's all like swamp vegetation and it was bad. The coherence is horrible, as expected for Sentinel. And I didn't get much. I didn't get much of any real phase signal except for this. And I zoomed in on that. And I'm sorry, I know I'm dovetailing a GMT course. And it's just like snapshot pictures. I apologize. This death march of a course did not give me enough sleep for me to work on making scripts in GMT5. So yeah, so these are, I hear you. So these are some images from Google Maps overlaid. So this is Momotombo volcano, which is, I forget the name of the lake, but it's by the lake. It's actually a very active volcano. Even the Google Earth imagery, you can see a plume there. And in the InSAR, I was surprised, something jumped out. There seems to be some inflation there. So the scenes that I used were 2 months apart, roughly. And I was really surprised that something popped out. Now, it's my job in the lab to actually monitor this. So when I sent it to my supervisor, he's like, well, why didn't we know this? So yeah, so I processed the GPS data and I pulled up some data. And it seems as if there is some signal, like in the, what's 0.39? I'm going to say early April, late May, late March. But there is some change that is happening here.
Where is the GPS?
The GPS is Mom 0 right there. Yeah, sorry. Well, it's on the flanks of the volcano. It's there. And last night I was trying to get a velocity for this and I was just falling asleep. And this morning I realized, I thought it was garbage, but this morning I realized it makes perfect sense. So this is the velocity. This is just in a linear fit of this bit here, the horizontal. And it's definitely inflation. So there is something interesting happening there that I accidentally found because I was not looking for it. I was just looking to see how much correlation, coherence I would get in Nicaragua using Sentinel-1A, ascending orbit. And that's it. The serendipity right there.
I'm just curious about why there has good coherence, but the rest.
Volcanic edifice, man. Like the plume creates acid rain, it kills everything around it. If you look at any volcano, you see that the edifice is just like lava because the acid rain kills all the vegetation. So it's perfect for volcanologists using InSAR. Yeah. Yes. We don't talk about it. We don't talk about the vertical.
Why don't you talk about the It's not as accurate.
It's not as I mean the scatter here is horrible. This I purposely cut it to a year, but the vertical is not really that perfect. I mean, and in Nicaragua there's a lot of hydrological loading, and this actually spans the beginning of the wet season. So there might be a lot of seasonal signals polluting that.
What's the magnitude of
I tried, and then I got confused last night. Do I divide by 2, 4? It's about 1.5 fringes. Yeah, so that's 7.
3, but then
No,
the look angle.
then the look angle. Yeah. Well, 7 or less, 7 to 0. It's possible. Well, I know it's not rain because this, I mean, you can clearly see the semi-annual signal, well, the signal here. This is a breakaway from what's ever happening here. It could also be a slow earthquake. I don't know. It happens all the time in this part of the world. Yeah.
So one thing about these volcanoes is that they stick up. How tall is this one?
I don't know. I'm not a volcanologist.
Because when they stick up into the atmosphere, this could possible there's an atmosphere.
That's what I thought. Yeah.
So the only way to test that is on the way home on the plane, do a couple more interferograms at different time intervals.
Yeah.
And then sort of confirm that
it's an actual signal.
Because you did get one that goes the other direction. But,
Yeah.
But really, it wouldn't take much to figure out.
No. So yeah, I'm going to do a time series analysis.
Yeah.
When I get back.
You just do 3 or 4.
Yeah. But yeah. Should I show what? Sure. Yeah. So I mean the edifice is here. So I mean, yeah.
If you know how often they acquire data, when you did the catalog search,
For
do they get data every 6 days or?
For this region,
Yeah.
I did not make note of that. I honestly had very low hopes for it working. Okay.
So, yeah.
All right. No, I'll certainly look into it. I mean, it's important. Yeah. Anyone else? All right.
Great, thank you.
Who's up 1 more 3 here? 4. We had what? Yeah. So I'm going to make this into a PDF file so that you can show the whole screen. Or do you want to plug your computer in?
No.
Okay. All right. So Yao has sort of done this as a service for GMTSAR folks who want to do grounding line. This is not her real research project, but it's worked out pretty well. Did I save it in the right place? Where did it go? I'll do it again. File, save. Export. PDF. Put it in desktop. place. Okay, it's right there. Can I see it? Yeah. Right here. And then I go to view, full screen. Okay.
So I'm going to talk about the grounding line. Grounding line is basically the boundary between ice shelf and ice sheet. Here in this figure from Leo, I showed the three major ice shelf and the region I'm going to look at here, somewhere in Rose ice shelf. Basically, what to go to the
I don't know, how do you advance it?
Oh yeah, I see. Okay, so the grounding line, it's pretty hard to measure it by in-situ measurements. So scientists use a satellite to see it. And it is basically where the ice detaches from the bay and becomes afloat in the ocean. And for the ice shelf, the major motion on it is the horizontal glacier flow driven by sliding and gravity, and the vertical motion influenced by oceanic tides. And the horizontal flow is pretty steady and strong. If we make a single interferogram, we can see a lot of fringes. And besides topography effects and noise, these fringes are basically caused by the horizontal flow and vertical ocean tides. But if we double difference two interferograms, and basically we can assume that tidal conditions are different. So we can like cancel the horizontal flow and get the vertical motion of ice shelf, because this ice sheet part is stable and only this part will move up and down. So here what we do is I choose three things of from Sentinel-1, and there are 6 days apart, and use this SRTM 15 topography data. It's not a very high resolution, but the result turned out to be pretty good. Okay. So and we would expect to see the grounding line where it can be separated by a typical pattern of dense fringes. Okay, here are my results. There are 2 single interferograms that are 6 days apart, and if we make a difference between these 2 and wrap the result to minus pi to pi, and here's a double difference result. And this thin white line is a grounding line that I got from someone. I'm not really sure how they get the result or how old is it. But we can see the InSAR result agree with it pretty well. Like for these 2 single interferograms, we can see a lot of fringes that are major caused by horizontal flow. But here, after we cancel the glacier flow motion, we can see the vertical motion in the line of sight direction. What I found interesting is that even though we don't make the double difference, just looking at the correlation, it basically shows the grounding line pretty well. And we can even see the path of ice flow, see where
because the flow motion is pretty strong and it will make the correlation pretty bad. These are basically my results. Yeah, I just want to make a single double difference result and to see if it will work well. And I'm not going to make a time series, but it will be an interesting topic, I think.
Any questions? Do you have any glaciologists there?
Basically benefiting from the fact that it's correlated to the water is because it's like stable flow to measure where that line is.
Can you say it again?
So is it the side that's ahead of the round line is yeah, that most liquids are correlated during the paragraph. So
Yeah.
the technique is basically using the correlated versus consistent to measure that. Is that did I get that right?
Well, if you look at there's two interferograms that are just single difference. And like here, the correlation's really good. So this is all ice. All of this is ice. Like that's ice. So it's just decorrelated because it moved vertically a lot. Yeah. I mean, people do this with InSAR, we've done them a lot, and they do it with LiDAR profiles to find the grounding line. But people don't think you can do it with Sentinel because it's 6 days apart and they want to have like 1 day. So, but it seems to work really well.
Yeah, I think Eric Renewal has been using like InSAR, like ALOS or EIAs to map the grounding line since the 1990s. Yeah.
He's using ALOS, which has a longer wavelength and infringes for the product.
Yeah.
But this works really well. I mean, so we're going to try to make an example put into the GMTSAR distribution so other people can do this double difference.
Yeah.
Thank you.
Okay, who's up next? Matt. Oh, and it's a PDF file. Look at that. That's nice. So this is another sort of exploratory thing, right?
Started yesterday or 2 days ago? Or, yeah. Okay, great. I like these. I have no idea how it's going to come out. Okay, thank you. Oh, you need to get your hold on. Your certificate. Yeah. This is important. Yeah, mine. Show mine. Yeah. Put them over here and you can grab the right one. Yeah, show it to Mike so he'll know that you're yeah, yeah. Is he your advisor? Yeah. Okay, yeah. Thank you. Yeah.
Okay, my name's Matt Burgess. I'm going to talk about deformation at Mauna Loa. This is a topic that I'm familiar with. I worked for the Hawaiian Volcano Observatory from 2013 through last summer. And I missed good burritos and surfing over sand, so I moved back to San Diego. So some background. Between 2013 and 2017, there was deformation on Mauna Loa. This butterfly pattern, which is partially obscured by the plotting of these earthquakes here, is present along either side of the Mokua Veoveo caldera and the upper Southwest Rift. And these are data between 2013 and 2017. It's a Cosmo X-band radar, and it shows about 15 centimeters of deformation. Between this time, there was about 7,000 earthquakes beneath about magnitude 4. There was, I think, one magnitude 4.1 on the south end of the caldera. And most of the earthquakes are about magnitude 1. And the spoiler to this and why I went after it is because I've spoken with people that work for the volcano observatories, and they've told me this is happening now. And so, the signal is present if you massage the data correctly. I'm not sure I did. So this is a plot of earthquakes since 2013 on the far, I guess that's the left if you're looking, is January 1st, 2013, and the end is present time. This is earthquakes in the summit area of Mauna Loa. Basically that same area that was shown in the previous figure. And you can see there's an increase from basically a background of about 0 earthquakes to like a high rate in July of 2016 and another fairly high weekly rate in July of 2017. And then it tailed off. It went down to almost nothing. And then Kilauea erupted, and during the eruption, some earthquakes started happening again on Mauna Loa, and since that time, the earthquake rate has increased significantly. It's the highest it's been during this episode of unrest that began in 2013. And there's been about 3,000 to 4,000 earthquakes in the past year. So compare that to 7 over 4 years, it's picking up. So here's a Sentinel-1 ascending interferogram over Hawaii Island from October of 2018 to June of 2019. And I was recommended to look at this larger time frame to catch the deformation that should be visible in the InSAR. The seismicity is plotted, and that's current seismicity over the past year. And it's got a similar pattern to the seismicity. You'll see it in the next slide better of the previous episode. I don't know, this is the kind of thing where I could convince myself that I see a bit of a fringe here that's parallel to the rift or to the southeast of the rift. I'll zoom in to see a little better. So these are the earthquakes. There's the caldera, this upper southwest rift. These are reviewed locations. So there should be a butterfly pattern. So I kind of know I'm trying to find one, but if I didn't know I was trying to find it, I don't think I'd say there's anything here. And in fact, this is an area of high noise. This decorrelation down here is an area where there's coffee plantations and just kind of forest. Otherwise, this stuff is all basically above the tree line, but it does get a lot of clouds. So this picture here, you can see a cloud bank on the middle slopes of Mauna Loa. There's the summit, and this bank comes in basically every day. And these Sentinel-1 images were done at about 4:30 UTC, which is 6:30 p.m. in Hawaii, which is prime time for atmospheric noise. So I'm guessing that this signal here is mostly noise. And might have a little bit of deformation underneath it. It could be the sort of thing where you could stack it and get it out of there. But I'm not going to go submit an abstract to AGU or anything based on this. As this jumped out of me and I couldn't help but take a closer look. I wasn't trying to step on Lauren's toes or anything, but had to look at Kilauea because it's got some really cool features. You get a butterfly feature, which is typical of inflation due to a dike. But there's some interesting stuff here. This thing's hard to use. Maybe this is better. So this is the South Caldera. Halemaumau's right here. This is basically the inflation center of the summit magma chamber is located right here in the South Caldera. I know from personal communication with Sarah Conway at HVO that there has been deformation, inflation since March of this year. And I'm pretty sure that's what this side of the lobe is showing. But this is where looking at these fringes makes my brain hurt and shut down. And I was trying to run the unwrapping last night and it failed. But I think what over this long time span from October to June, was this northern lobe is actually showing subsidence along some pre-existing faults. And down in here might just be a little mix of signals between inflation and deflation. But for instance, the Kilauea Iki fault is right here, and you can see a little fringe right there. This is right here, south of Kilauea Iki as well. But this is right on a scarp right here. This is a fringe that's outside of the park boundary in Volcano Village. And during the eruption last summer, there was earthquakes lighting up this fault. So I believe that's real, and I'm guessing that's probably a subsidence source and not something that's going to inflate, especially this far from the inflation source. And then also this fringe out here is parallel to, or at least breaks on, the Kauiki fault, which is basically the separation between Mauna Loa and Kilauea. So there's a lot going on in this interferogram. I definitely want to spend more time looking at more, breaking it into more shorter time intervals and seeing where subsidence stops post-eruption and when this inflation begins and how that changes. And then this big purple-blue blob in the Southwest Rift is interesting. I'm a little, this is where I wish I got it unwrapped, because if I knew for sure that that was away or down, which is what I think it is, I would, my hypothesis is that that area was blanketed in ash during the eruption from all the explosions. And I'm guessing that it's also a downwind going from northeast to southwest. That's the prevailing wind. So my hypothesis would be that that is, the ash got scoured away, and you're maybe just seeing a signal from just kind of aeolian transport of ash that's no longer present. It was pretty deep right after the eruption. So that's that. Tried to look at Mauna Loa, looked at Kilauea. Yeah, that's, so in this island view, you can pretty much map the vegetation with the incoherence. This is thick forest over here, thick forest over above Hilo. This is where you get your Kona coffee from over here on the west side. Other than that, the island, especially the west side of the island and the summits of the big mountains are totally barren. So this is atmosphere aside, it's a good spot for InSAR. It's definitely what HVO uses to monitor deformation in addition to GPS.
Is there someone at USGS that's doing the same thing at Mauna Loa, you know?
Ingrid Johansson's the research geophysicist now. Asta Miklius is retired and still working adjunct kind of, but Ingrid's in charge of that, and Mike Poland stays busy with this as well. So they've made these interferograms, and there is, I don't know if it's this good, I don't know if it's the same satellite that they've been using, but there is a butterfly pattern that's currently being displayed over the last 6 to 8 months.
Is there XR data? Super sites?
I'm not sure what they've got.
But even with Sentinel, after the eruption, they started imaging it every 6 days for both eruptions. I think are they still doing that? Yeah. Yeah. So again, if you had time, you could easily go through the whole suite of images, and you know exactly what Mauna Loa is doing.
Yeah, I was definitely limited by my computer's capacity. I was deleting photos and things as I was trying to trying to run. It's backed up. It's now I'm just deleting family albums for science.
If you go to Ash, it's going to be okay.
I don't know. That was just kind of like this was,
That is.
I don't know what to think. That is down. So I can't.
The face is going up.
Yeah, I can't imagine. It's weird because it's over such a broad area. I don't know that would be why it would be down for one, and I don't know. Maybe it is. Maybe it's something in the rift. Maybe the Southwest Rift actually drained a little bit after the eruption as well, because the Southwest Rift was pressurized prior to the eruption. There was a lot of earthquakes occurring further southwest of here, kind of at the end of the Southwest Rift. So yeah, before the eruption, we were like, where's the next thing going to happen? And the Southwest Rift is definitely a possibility we're thinking of.
Is
So
Mau still moving up and down a lot?
I think I think
It went down like 400 meters.
yeah, so that's done, I believe. It might just be like kind of falling in on itself, but there's the inflation signal that is real. Yeah. So maybe that is an actual signal. It's pretty small. Well, that would be. Yeah, that'd be probably along the south flank. And so it kind of goes into like a normal fault into the ocean off which is Mackay of the rift. I don't know. This is pretty far up, pretty much in the summit. So that's definitely caught my eye. If I was to keep plugging on this, I'd try and look into that and see what that is. And that also in the caldera bounding stuff is really interesting to me as well.
Yeah, with more data, you could definitely know the answer.
Yeah. Might just have to do a PhD. All right. Thanks.
Okay, thanks. All right.
Feel free to take breaks and get coffee and so on. Chen. Oh, yeah. Okay. Let me change this to I'm going to make it into a PDF file. Oh, yeah. You can use Google. Yeah. Right here.
Now that we know how to do full screen.
Okay. Good morning, everyone. My name is Chen Zhang. I am a PhD student from George Mason. Well, to be honestly, I've never used the SAR data, and I have no experience in the GMTSAR before I come here. I mainly work on the land use land cover change, crop mapping, and some GIS and web development stuff. So, well, I want to take this opportunity to thank all the instructors, developers, and the students for, offering this very informative short course for the beginners like me. So this is my presentation. And here's the outline. I'm gonna talk about my mini project in these 4 steps. First, I'm gonna talk about the data that I use in this project and the processing using the GMTSAR and the results and some of my future works. First is the data. The study area I choose is the Cape Town of South Africa. The reason why I choose this area is because I'm currently working on another project. It's about to detect the slum area in the developing country. from the remote sensing data like Landsat and Sentinel-2 data. So, and the cat town of the South Africa has a lot of slum area. So it's a very good area for the slum detection study. So I choose this area as the region of interest. And so the first step is downloading the data. And I downloaded the Sentinel data from the Alaska satellite facility because it's much faster than the Sentinel data hub. So I download data, and this is 2 data I download from the 2 Sentinel data. The first one is captured by the June of last year, and the second one is June of this year. So this is 2 data I download, and the orbit data I downloaded from the InSAR website. So this 2 data correspond to these 2 Sentinel data. So this is the data I download, the star data I used in this study. And this is a preview of 2 data, 2 star data. And the DEM data, I tried to download the DEM data from the GMTSAR website yesterday, but keep processing and cannot be done. So I downloaded data from the open topography. Actually, this web application is running by I think it's a San Diego supercomputing. I think it's running by the university. So I download the DEM data, and I see the DEM data in our sample data set is in the grid, the format of grid. So the data I download is GOT, so I just converted format. And this is the coordinates of the DEM. And so this is the DEM data, and this is the visualization of the DEM data. So we have the this is the file structure, the directory tree of the data in my project. Basically, there are 2 Sentinel data, Sentinel images, and 2 orbit files, and the GM files in the topography folder, and some configure files. So, and for the processing, I just mainly referred to the this LA sample data set because there are so many parameters in the configure file. I cannot, I'm not able to, figure out all of them right now. So I just changed the data and mainly using this configuration file in this sample data set. And this is 6 stages. So I just copied from the from here. So basically, in this project, this project aims to process every substrate and merge all the resulting interferogram. So, and this is a command line that I use, and just change this the file names, and this is a this is a configure file. And I just run this command, and it takes around a couple of hours for processing this using this GMTSAR on my laptop. So, and then I got the result, and this is the result from the F1 folder. And we have some with the correlation amplitude and phase image. And well, to be honest, I don't know how to read this data yet, so I will try to learn the SAR analysis in the future. But this is the result, and it looks right? It looks right. So, and this is in the F2 folder, and this is the third one, and this is the final result. Is basically it's like after the mosaic, and it's the merged result. And here is a face image of the this is the South Africa Cape Town area. And the future works, I this is my 3rd day learning the SAR data. So in the future, it's a long way to go. I have to keep figuring out all these terms and start learning the analysis on the SAR data and softwares. Yeah, and speaking of the GMT, I found the GMT is a very, very powerful tool for the mapping. And actually, our center running some, operational system for hosting the data of like USDA and USGS. And here are some screenshots of our application. And our application provides the capability of the on-the-fly PDF generation for users to generate a map like this. So actually, in the future, we consider, maybe we can integrate the GMT in our server end to power this like on-the-fly mapping thing. So which is, well, it seems like Doc agree with that. So, yeah, he likes that. So, so yeah, it should be a very good idea to integrate the GMT to our web application, and so we can provide users more flexible APIs and to make a more beautiful maps. So maybe we can implement the GMT as a web service in the future to improve our apps. So well, that's it. Basically, it is. So thank you.
This is obvious. Exactly detect slum from something like
Slum? You mean in the detecting slum?
Yeah.
Oh, okay, that's a different story. Yeah. So if you're using machine learning, it's gonna be very easy because you can just feed the sample, like you can find a lot of sample images for the slum area and feed the sample in the model, and model will learn by itself. And then you use the model on somewhere else, and you can get a slum map. So something like that. So
for Cape Town, I think it was Cape Town you were showing, right?
Yeah.
Is there any groundwater use there? I just almost saw wells and groundwater.
That's a good question.
Go back to your last.
You're in a paragraph.
Oh, in the program, okay. Let me.
Yeah, that came out pretty well.
Yeah, I was looking up by Cape Town. It almost looks like that being groundwater. Or I don't know.
I actually don't know.
Yeah.
So you were interested in this. I'm not familiar. Oh, there's Cape Town.
Yeah, Cape Town. There are.
See that there? That's what you're looking at.
Yeah,
there.
that's why I don't know.
Yeah.
Groundwater extraction there.
Yeah. Are you interested in where people are pumping groundwater?
I don't know actually. We just detect the land use.
That does look sort of like, yeah. Every time we make interferograms, we see someone pumping groundwater, the surface goes down.
Oh, really? Okay.
In Los Angeles, everywhere.
So any other comments?
Yeah. Maybe on your flight back, you can process the rest of all of this.
Yeah, hopefully. Yeah.
Yeah, it's pretty nice, actually.
Thank you.
What is this? This is all,
okay.
This is probably atmospheric stuff. This is all, this must be cropland or somewhere there.
Yeah, that would be cropland.
Campground, that's a whole year, so that's pretty good explanation. Questions? So it sounds like the GMT people need to start making on the fly. Put it on your to-do list.
No, we can implement it in our server. We don't have to do that. We can,
Yeah.
I think you can, because most of the things are actually in water, especially the backtrack.
Okay.
Yeah. Yeah, if you just wanted to do that one little area.
Yeah.
You might be able to fit it on your laptop.
Oh, yeah, sure. Thank you for that. Okay, thank you.
Hey, what we got here? So we're down to Zheng. Do you want to do the Google thing? Maybe Google's better. Oh, did I just close that? Ah. Oh. File, let's see. File, new, window, Google. Was it here? Or do I have to log in again? Sign in. Presentations. This one here? Okay.
How to get in full screen?
I don't know how to do the full screen. You guys, how did you make the full screen? Open with.
On top of this. Oh. Right. So I'm Zheng from UC Berkeley. I'm a PhD student. Basically, I use GMTSAR to observe very large spatial scale pore-seismic deformation. Oh. Yeah. So this is my study area. This map shows the general tectonic setting around the Tibetan plateau. So my focus is this fault is a very long fault. It extends about more than 100 kilometers from west to east. So on the western section of this fault, very big earthquake occurred 2001, having magnitude of 7.8. So the red line shows the very long surface co-seismic rupture on the surface. So basically, if you want to observe the post-seismic deformation following this earthquake, you need a very big set data. So basically, I use the almost 1, 2, 3, 4, 5, 6 frames to cover the whole seismic area. So now I'm processing the data on this track. So basically, if you because the post-seismic deformation is much smaller than co-seismic deformation. So if you want to extract the very weak post-seismic signal, you need a lot of interferons. So this is the interferon networks on one side. So basically, if you want to capture the post-seismic deformation with a lot of deformation, so you need to generate interferon with a very long time span. But it's a very trade-off question, because if you have very long time period, the interferon will suffer severe decorrelation for the signal. So yeah.
How do you make that plot?
Yeah, it's in GMTSAR when you do the time series analysis.
Oh, for time series.
Yeah. So this is all the interferon shows. Generally, to capture the deformation, you have to use the very small spatial baseline, and then you choose the temporal baseline based on your different focuses. So this data covers almost 4 years following the earthquake.
So you selected all those by hand?
Yeah.
You selected them.
So
So basically the scripts are still running. So I only have this interprogram. So what we can see from this interprogram, so it's consists of two frames along one side. So this line is the report. You can see a very clear linear structure here. So if you just use interprogram, actually you can see nothing because it's featured by long wavelengths atmospheric noise signal across the whole frame.
Are those features in the bottom right, are they artifacts or?
This one? Yeah. I think it's because they have some more problems during the alignment.
Okay.
Yeah.
I'm sorry?
This area, the mobile files, I think it's
Oh, okay.
So maybe the ionosphere.
So those areas are graduation optimal, so you know it's concept, like it comes from one word to another word. You can remove it lines by using line compounds or
So sometimes if we use interprogram to observe the co-seismic definition, if the displacement is very large, you can also see this jump. Yeah.
And so you remove the trend on the one on the right. I mean, are these the same interferogram or are they
Different.
different?
Yeah. So, but you can see a lot of this feature adds a lot of interprograms.
They both have the same east-west feature.
No, I here just want to show we have a long wavelength signal.
Yeah, but I mean they both have that.
Yeah, actually they are similar, but similar. Maybe because they some signal definition. Yeah, so some areas they have the correlation because it's a lake area.
I mean this very prominent feature is the same in both. But do they share a common theme?
No, different.
Different.
Yeah. So I think the form is still creating. Yeah.
Okay.
Maybe 12 millimeters per year. But that is the interseismic slip rate. For post-seismic period, maybe it's larger than that. Yeah. So, but for some other interprograms, what you can see is only very short wavelength signal because of a turbulent atmospheric noise. Yeah, so hopefully the common sense stacking method in GMTSAR is useful to mitigate this phase noise. Yeah, that's all. Any comments?
I have a question.
Yeah.
You showed a lot of data there. That's not sitting on your laptop, right?
Yeah, not a very powerful computer.
It's a computer of a person.
Yeah, working.
And you just started assembling the data, or you showed like 4 interferograms.
Yeah.
Have you made hundreds, or is this just the first 4?
More than 100 interprograms.
Oh, you made more than 100.
Yeah. So it's running at a step of time series and last step.
Okay.
Yeah.
And you work with Kang?
Yeah.
You do it on a supercomputer, or?
They have supercomputer, but I don't use that.
You don't use them?
Supercomputer.
You use the supercomputer. And how much disk space did you take? How much disk space did you use?
Very large.
Like terabytes, 20 terabytes.
Yes, sometimes it depends. If you process this data and you have delayed some files and then move forward.
Yeah. I see.
Yeah.
So you don't have enough space to put it all there at once.
Yeah. It's also time-consuming work. Any questions?
to give us an update, maybe at AGU. Will you
Maybe.
present this at AGU?
Maybe another project, not this one. Yeah.
Because you guys were asking how much space it takes.
Just buy a bigger disc. All right, so who we got? Jay, you want to do it on Google again? Okay, Google's the winning display platform here, definitely. Oh, did I close it again? Oh, man. Did I close it? All right, well, how do I keep doing this? Keep closing it. Wait, sign in. I'm amazed it never asked for your password. I think anybody can go to my Google Drive and do whatever they want, you know.
Version 2.
Oh, okay.
Right. What's that? Oh, yeah, Google Drive. Put it all out there. PSD says we have as much space as we want.
Right. Today I'm Jay Kim. I'm studying geophysics at Stony Brook University, second year PhD student. And today I'd like to present both seismic deformation associated with the 2019 earthquake in Ridgecrest. Here is GPS data. It shows really cool feature of that earthquake. And I looked up GMTSAR page and they posted this horizontal motion inverted from InSAR data. And the pattern is very similar to each other. And so for the first time, I took the example data for Ridgecrest earthquake and I processed and I got this image here. And then I moved on to post-seismic period. I used two InSAR data. One is for July 22 and one is from July 10. And these are both ascending. So I thought it could show good post-seismic. And when I get this for the first time, I was actually looking at this part and thinking, oh, it looks cool. And Eric just came to me and this is wrong. And you had a smaller elevation model. So I was like scratching head and he just pointed out your fault is somewhere here and it shows something. And it was like
Basically, what you're saying is that this, when you made your DEM, it only went up to this.
Yeah,
okay.
Like
Yeah,
this.
So that's what a DEM,
Yeah.
you don't have a DEM.
And it was like a sonogram for parents who have their baby for the first time. So yesterday night, I was looking at this again and I lost where fault is. So I had to plot Foucault mechanism on it to figure out where it is. And here, this is unwrapped the phase here, and the signal is a lot clearer here, but still it shows some trending there. So I use GMT GRD trend to detrend the unwrapped phase map. This is it. And then I convert the system to latitude longitude system and plot them together here. And this is the Foucault mechanism of magnitude 7.1 here, right electoral. And then I got the LOS data here. So this is microseismic image, and scale is a lot smaller if you compare to this image from GMTSAR webpage. This is image between 2019 July 4th and 18. Yeah, Eric produced co-seismic. Yes.
So did you add, I'm sorry, Eric, did you add to smooth it? Like several before and after, to average them? So that's just from one layer?
It's a big signal.
Yeah. It's about 800 to minus 800 millimeter. Right? Mine is from like 30 millimeter to minus 30 millimeter. But what I found interesting is the pattern is very similar, which is makes sense. They moving away from satellite here, and they coming close to the satellite, which is we also see in co-seismic pattern here. So I plot the line of sight direction with the pointing vector here, and focal mechanism is right here. So yeah, this is it.
Yeah. Thank you. It's all brand new.
For plotting the trajectory, how did you get the range and azimuth from the SLC file directly?
Oh, okay. I didn't calculate. I just look up other image and I try to draw as close as possible. So it's totally arbitrary, but I know it's ascending and looking right direction.
So, yeah, because it's looking off to the right, like this.
Yes.
It's really hard to see any strike slip motion. Yeah. This is probably mostly vertical. Mostly kind of vertical.
But is that the same in the co-seismic maybe?
Right, and this is about plus minus 30 millimeter. And yesterday I looked up a couple GPS fields, horizontal fields, and the maximum is like 5 millimeter.
But the GPSs are really far away.
Yeah,
Far away. So why did you, if you go back, maybe you didn't need to be trending.
Here?
Like this. This is without the trend. Wait.
That's without the trend.
Without the trend. Oh, you can see a very sharp break here.
It's about double.
Wow. So that's the fault right there.
Right.
And then this whole thing is going down because the range, this is unwrapped phase, so the range is increasing on this side and it's decreasing on that side. So this whole thing could be going down by 8 radians.
About 5.
5 centimeters.
Yeah, 5, 6.
Or,
Yeah.
I mean, you might need to be trended, but I don't know.
Eric, you talked about something here.
Yeah, I don't know. So I think Kang tweeted this in a program. Did he tweet this one, Kang? No, Kang. Does anybody know how to run Twitter? So if you go to Twitter,
I don't use.
You don't use Twitter? He's a good Twitter user.
You started.
I learned. You're good at Twitter? Okay. So what we need to do is Kang Wang made a post-seismic interferogram like from this date, I think. We should get there. I saw it online. It's I was looking at my tweets.
You wanna do it? I have no idea about it.
I'll try.
There.
So, oh, there's a Twitter right there, but I'll go to a new one. Okay, oh, Twitter's there. Do you have to sign up? You don't have to sign up, right? Sign in. Somebody posted a Twitter on a post-seismic. Oh, Roland Bergman. Roland did. And he said Kang made it. So do I have to sign in or can I just go there? How do I get there? Right here, or
So you need
okay? Okay, Bergman, Ridgecrest, seismic. I don't know if you used the same pair that you used, because it would be possible to go further. Wait, that's ascending?
that's
Yeah, that's the third pass after the earthquake. I don't know.
July 22.
Now what happens? Now what do I do?
No, I tweet it to your search.
Oh, Twitter. Like that?
Without add signs.
Just Twitter. Take out Ridgecrest. Did I spell Bergman right?
Yeah.
Huh. Maybe Twitter first. Maybe we'll just go to Twitter. Twitter.com. How do I get in here? Just, I could sign in. Twitter and then Bergman. Did you find it? Really? Maybe I was dreaming. Yeah, okay, here we go. Now I just scroll down and his. Oh, maybe it's not the right Bergman. It's Roland. Roland. There's a retweet. Well, we could decide it, but anyways, I think he. Did you find it, Eric? Anyways, those are really interesting results because it's like the first post-seismic, and that's sort of what you expect from all these. After Hector Mine and Landers and so on, there's that sort of after slip on the fault, not the right size. You could keep making interferograms every 6 days, and so a bunch of people have been deploying GPS in the field for this earthquake. But the problem is you can't get near that part where you showed because it's on the base. So all the GPSs are around perimeter, and they're going to see a very small signal, and the big signal is going to be right where you saw it there. So, yeah. Anyways, it's interesting.
Thanks.
It's new stuff.
One thing to do is
Ignacio, do you want to use a PDF or Google or PDF? Okay.
I'm sure I saw it. It wasn't a dream. Yeah, maybe what do they call it? Snapchat? Snapchat where you take a picture and then it disappears.
That's okay. Well, hello, everyone. My name is Ignacio Garcia. I come from Ensenada. I'm studying at CISESA. I'm studying my master's in seismology. So this is the topic that I selected, monitoring lab subsidence by using InSAR, or in this case, GMTSAR. That's okay. Okay, how can I go to the next one? Oh, that's it. Okay. The area that I selected to make this exercise is the, well, we have northern Baja California, this area, this is Sonora, is the border, and this is the area in what I am interested in, which is the Cerro Prieto geothermal field, which is between the Cerro Prieto fault and the Imperial fault. Then this is a step over Cerro Prieto. This is an aerial image of that area, and this is the volcano, which is right here, more or less. Okay. Well, what did I do these days working with GMTSAR? The steps that I followed, well, I downloaded the data. I used the Alaska Satellite Facility to get the data. I selected those data sets from June 11 and June 23. It's a span of 12 days, exactly. Then I got the orbits in Sentinel-1 QC, quality check. After that, I follow the steps, generate the theme files, create a topo directory, adapt the process line, which makes everything. And I have to understand better because actually I'm new on this. I didn't say it, but I'm new. And generate an interferon. Finally, I applied the Snafu CSH to unwrap the face. Fortunately, it worked. Well, and this is the result that I got. I have seen many interferograms from this area. All of them are really cool. This one, not much, but well, that's what I think. But as I said, I'm new, but I'm happy because this is my first interferogram. And looking for something, trying to make an interpretation of this. Probably here we have atmospheric data. I don't know. I think that we can see the fringes, 10. But as I said, this is my first one. I'm new on this, but I'm planning to do many things. So we can see a low coherence there. Well, that's it. Then we have the correlation and the phase, azimuth gain range, which is the same that I presented first. Okay, I'll continue. Then I unwrapped the phase and I selected this area. Just making an approximate to the place where I'm interested. But I cannot say too much about this, but well, this is what I got by using GMTSAR. And as I said, I have more things to do, learn more about this, but I'm really happy to do it. So first, I want to thank Dr. Sandler for lending me your laptop because I couldn't do this on my laptop. But well, I need to make it work because I'm going to need it. And finally, thank you all. Thank you, the GMT group. And this is an aerial image of Cerro Prieto geothermal field.
What was the time span of that?
12 days.
12 days.
Yes.
Okay. So how much?
There was something interesting that yours was.
How much substance? You're going to get anything? 12 days. But yeah.
Well,
just the first interview.
I think what I thought is that there is a high rate of subsidence.
Yeah.
So probably in a few days we could see something that I was just experiencing. I don't know.
But there's definitely a huge signal here.
Yeah. Yes, absolutely.
Was it correlated? If you go back to the correlation map, you had one with that. Yeah.
That one.
Where's the geothermal site?
The geothermal is here.
Right there.
This is the lagoon
So that's the
of
pond.
operation. Sorry?
That's the pond, the geothermal pond.
Yeah. This is the volcano. Yeah. That's it.
So I was just kind of curious. Have you ever looked at the Pinacate?
Oh,
I
only
always wondered if there's
this part.
over there, if there's ever, there's some volcanism last 2 centuries there.
Yeah.
So I'm always curious if there's any information.
Well, I don't know what to say, but we can see that we have a really good correlation. So we can do something there. Probably. Just for practicing.
No, we did a geology field trip there. San Diego State.
Well, what I know, there's people planning to put stations in that area, GPS stations, so we can have more information to validate InSAR data.
So you work with Alex, right?
Sorry?
You work with Alex down in.
Yes, yes.
And you've installed some permanent GPS stations. He has all around.
Yeah, all over this place.
Is there one near the geothermal, or you can't get on? Is there a GPS station on the geothermal?
No, that's unfortunately not.
Yeah.
But close to the geothermal field, there are a few of them.
Is even walk us through one of their strain meters along the fault?
Well, I don't know how to answer the question because it's complicated because this area, well, it's complicated to me. Yeah. But this area, because of the anthropogenic activity, the tectonic activity, because it's the step over, also due to those two faults, I don't know how to pronounce it now. It's the question. Well, I didn't say it, but this is the area where I'm planning to do my thesis work. Yeah.
So you'll gather all the sentinel data for the whole time.
Yes, well, but the new thing here is that we're planning to use UAV-SAR data.
UAV-SAR.
Yes. To get another direction of the loss.
And then Alex going to get a big computer.
Let's see what happens.
You will need like a really big computer.
Yeah, there is a big computer that's accessible.
Oh, okay.
Yeah, we have it work. Okay.
Thanks.
Oh, thank you all.
I want to close this. I can just go back, right? I end the show. Okay, you Google guys, how do I end the show so I don't have to log in again? And escape? Nope. You know how I end this thing? So I don't have to keep going back and logging in. Start a show, but you can't end it. Escape. Right click. Oh well. Okay. Roman is. Oh, is that remote? Oh, that's you guys. Yeah, yeah. Okay. Do you want to use the PowerPoint or it's not on Google, so we can just make the PDF. Okay. Let me go back. You sent me a PDF.
Yeah, the PowerPoint will work as well. Either or.
Let me make it into a PDF because then the remote people can see it better. Export. Desktop. PDF. Perfect. Full screen. Okay.
And this is just like up and down.
I think you just moved something down. I don't know how it works. Page down.
I'm looking for it.
Maybe.
Oh, it's not in
that
now.
one?
No, that one's not working.
Mouse.
Page down.
Oh,
left and
left, right. Okay.
Hi, everybody. So just following from what Ignacio said, many thanks for the instructors and the organizers. We're going to miss you, or we're going to be running into GMTSAR problems, but many thanks. So the reason why we picked this event, this was a very catastrophic event, and I think there were about 400, 500 casualties as a result of this event. So of course it was well studied. So the event was has a magnitude of about 7.3, and this is the focal moment tensor results from the USGS. It has been extensively studied, and Rob Miller, he showed us some of the results. So we kind of decided, let's go with an event that has been studied so we could have a good feeling what our results should look like.
I don't think it's an extent. I would call it people.
So these are results from the Geospatial Information Authority from Japan, and these results here are from ALOS. And the figure on the left, I believe, is from the up-down displacement, and the figure in the right is quasi-east-west displacement. So it was a good thing that we could go for and compare our results later on. So I'm trying to compile enough information so when I go back home, we can become evangelists of GMTSAR and share it with others. So this is from the Alaska satellite facility, and I did a small box, and I saw that there were several frames and descending and ascending tracks. So this one in particular is the one that I'm gonna be showing first. And this is path 72, and it's from an ascending path. So these are our interferogram results for path 72. And you can clearly see large deformation on the right. And let's see, so we tried, snafu with the default 0.1 threshold, and this was the phase unwrapping result for this particular path. So we were kind of, there's a clear deformation on the surface, but it's not consistent with the results that the Japanese presented from ALOS. So we decided to go other paths and also other, the descending tracks. So this is for a descending, and I think I picked events, satellite coverages that they were within maybe 10 days apart. So they were fairly close together. So now, unfortunately, the deformation is almost on one of the edges of the satellite coverage. And this is the phase unwrapping. So we were kind of like happy to see this pattern was more consistent. It's gonna be a little bit difficult, but I'm just gonna go back to the Japanese results. I think this is more consistent with the results on the left, where you can see a down and up a static deformation near the earthquake. So there we go. So why stop here? So we tried another one. So we went again, and now I think this is the one that my colleague, Dr. Saikia, he obtained. And this is another descending path, path number 6. So we went and we downloaded those frames. And here again is the result. Now we are not so much in one of the edges of the satellite coverage. We have a better overlap of the deformation and the frame. So then we tried it again, and it's very consistent with the result that we had for the other descending frame. So something maybe later to play a little bit is to learn maybe how to do like averaging and stacking to kind of like clean up the results a little bit. So I think that's my last slide. So thanks again.
Which is the fault plane? What fault plane ruptured? Can we figure it out from the InSAR?
So I thought in the beginning that, most logical would be the high deep angle because it looks almost like a vertical deep slip. But those two, the strike will look like a little bit different. So I don't know enough if there's a way that I could maybe do like a combined representation, maybe to steer it where along the strike and see, because this looks like maybe that this will be where you will have maybe a fault, but this is not consistent with a vertical deep slip because one will be going up and one will be going down, which it's probably more like what you would see here. Oh, but that would be a pretty steep angle. Yeah.
So is it a steep dip or shallow? Arguably shallow.
No.
Yeah, but if this is colliding, I mean, if this is kind of like they're both in colliding thrust, so it's possible that it's also a very shallow, almost horizontal angle.
You know, there's a couple online tools where you can put in a fall parameter and put in the slip.
And those
Put
synthetics.
in the line of sight direction to give you the interferogram. I know Yuri has one. I think there's one at Riverside. Very funny. Lunchtime, you figure this out.
It's over 1 centimeter.
Yeah, one low.
So it's not vertical.
Yeah.
Also, really weird. It's very shallow. It's really weird.
Was this ALOS 2 data? Is that,
Yes, this is ALOS 2. Yeah.
you know, there are 2 directions. I don't see. What are the differences between those?
I think this one is up and down displacement, and this one is east-west.
Because
But it almost looks like the trajectory is north-south for both. Probably will be best for us is to download it and kind of reproduce their results.
Does anybody?
Oh, for Sentinel, I know for sure. So this one will be the ascending track, and this one will be the descending track. And this one we did it twice with 2 slightly different frames, and the results were very consistent. Oh, I haven't converted yet to like a line of sight displacement. Sorry, this is just unwrapped. Sorry.
It doesn't look like it ruptured the surface.
Yeah, so something that was kind of weird was that the USGS location is 19 kilometers, which is kind of pretty deep, but
yeah, probably not. What?
They're published paper. Did you do geodetic incursion?
Okay. It's already paper.
Yeah, they're paper. I think we saw. I think the main shot is kind of like these angles and the opposite. And the shower has is a different angle. And I think he's not at birthday. He also saw something. He did not hurt that.
yeah, this is big enough that somebody should have done like finite fault modeling on it. No, so the question is if we know the sensitivity in the displacement for the ALOS satellite. I don't know.
So you can take sums and differences of the 2 unwrapped phase. And I think that's what they've done here. So if you difference them, you primarily get the east-west component. If you sum them, you get a combination of north-south. So I think that's what they did here. Right? So the one on the right is the east-west.
Correct. Yes. Actually, in the observation take on each, there's an ascending and descending. So it looks like they took a difference from those 2.
Yeah.
So maybe the frames, they have very good overlap.
Yeah, definitely. You could do the same thing here.
Thank you.
Okay, so I wasn't dreaming about the thing from Roland Bergman, but it was an email. I guess Roland's not on Twitter. So how do I go? So I'll show you the post-seismic one that Roland sent to me, and it's now on the on this website, on the presentation area. And I keep having to sign into this thing. Ooh. I'm doing something wrong here. I sign every single time. Then we'll go on to the next one. I just found it.
Yeah.
Here it is. So this is the same. Can I make it bigger? Open. So convert. Open with. No.
Can you right click and do like view image to bring it like open? No.
Add comment. How do I make it bigger? Ah, did I wipe it out again? Oh.
No.
Well, I'll just drag it this way. So this is, I think, the same interferogram that you made. And how do I? Someone said you do this. Open with. I have it on my lap. I have it on the lap. Okay, let me download it. Over here. There you go, on the downloads, okay. Finder. So that's the, it's not much bigger, but I can make it bigger, I guess. So he put the fault on here so you could sort of see where that, so you had seen this subsidence thing here, and there's one right on the fault. So it's going down right on the fault. Sort of interesting.
So triangles are GPS.
Triangles? Oh yeah, these are GPS data. Pretty far away, yeah. Anyways, we can look at it later. So Roland doesn't use Twitter yet. See, I'm ahead of Roland. Now what's wrong here? That's downloads. Presentations. Come on. Here we go. So the, oh. Wait, do you want to use, sure. But the other people can't. Is there anybody on? Participants. Oh yeah, there's a lot of people on, so they won't be able to see. Do you want a PowerPoint or do you want it through the Google or? Do you want to send me the KMLs or no? Would that be too hard? Let's do it this way first, and then we'll plug in your computer. Okay. We can do both. So check. File, save as desktop. PDF. We have lots of time too. We have plenty of time.
Yeah. All right.
I heard lunch is coming later today, unfortunately. 11:45.
Hello everyone. So I have a very different topic. It's on using InSAR on detection water level changes in Everglades wetlands. Because normally we think of InSAR can do a cross, like this moving and deformation. But whenever you think of water surface, it's like decorrelated. So let's see how I use this to detect the water level change. Okay, so this is my study area. So it's the handle of the pen. So it's the southmost of Florida. This is the we call Everglades. So it's a really huge wetlands. There are different types of vegetation like wood, forest, and herbaceous. For my data, I choose Sentinel-1 data, and it's 12 days apart. I choose these 2 days is because we know there's lots of water management operations during between these 2 days. So basically, there are lots of gates, so people can open the gate and the water just discharge to there, and so there's water level change. And this is the principle. So basically, if only water, so there's only a single bounce, so you wouldn't see any signal. But when there's trees, so and water, so the trees can provide as a corner reflector. So the signal reflect on the water surface and bounce on the trunk and back to the satellite. So we can see actually a bright spot, like a brighter image. And here for the herbaceous also, if it's dense enough, so it cannot be very dense, but it can also provide as a corner reflector. So we are able to detect the using InSAR. So imagine here we have 2 times, one acquisition and after maybe 12 days or several days. And the range for the first day is like this. And the second day, there's the range, the phase changes because of water level change. So it's basically the principle. Now this is my result. There are many very interesting stories here. So I just name it with numbers. Maybe you just look at the interval 1, you can see there's lots of discontinuity. For example, here you can see the phase is not continuous. Like there's a shift here, like also here. And what's the reason? The reason is because of, oh sorry, it should be animation. I put these boundaries in different colors. They are different hydrological units. So we call them, like for example, here people call them water conservation areas because they function like a cell and they have a levee system. So they build this, so they can control the water level within this conservation area. So that's exactly why you see the discontinuity between these 2, because the water level can have even like 90 centimeter difference between the boundary. So it's like it's levee system. So it's blocked water. This cannot flow naturally. So that's why we see lots of continuity. And if you look at here, and there's fringes. If I can show you the Google Earth, you can zoom in and see more clearly. It's because actually here is a mangrove forest, and there is also topography like this. So when there's a tidal, this tide coming, and because we have 12 days apart, but acquisition time is about 11 p.m. It's on both days on 11 p.m. But it's not synchronized with the tide. So actually these 2 days, the tide is also different. And then if the tide synchronized with the SAR acquisition-based day, we wouldn't see anything because water level just same. So as the water level changes, we can see difference in the range. So we can see the tide there. Actually, if we use time series, maybe you can even see the tide, how it moves, the fresh water and brackish water. And also, so sorry, it's a little bit messy. So this is 2 identical image. I just so in the Google Earth, I just click this photo. You can see there is a gate. So it actually shows the point source here. The point source is like when the water, when I open the gate, the water comes in, and then the water level changes. So it causes this radiation pattern.
And that square pattern is the boundary of
Yeah.
the wow.
Yeah. So that's exactly the boundary.
Looks like an error in the interface.
Yeah.
And how much height change across that boundary? You know,
I'm not sure here. Here I'm not sure.
it's a lot.
Yeah. So actually, there's a Lake Okeechobee there, so the water flow from there, and the levee system control.
And off to the right, there's three little things.
Yeah, I'm gonna show in the last slide. So these are, I searched on Google, it's called covert. So it's basically the channels. And I just zoom in, like here is something. So it's showing the optical image. So when they open this channel, I guess, so the water just come in. This is from another Google image. It's not exactly here, but it's like, it's beautiful radiation pattern.
And the reason it's not uniformly flat
downstream
is it's flowing through the vegetation.
Yeah.
Sort of slows it down a little bit.
Yeah.
Creates a slope.
Yeah, there's a topography slope. If it's flat, then the phase should be the same. Oh, I just actually here. Originally, I want to ask you because here's animation. So here actually is the we call it Turkey Point nuclear generating station. So they generate have lots of nuclear waste. So what I find here, I'm not sure whether it's because of the nuclear wastewater, because here is the you can see it's the boundary, and we see the pattern here. I'm not sure whether they just discharge the water, the waste here, but we can.
In other areas where it's decorrelated, that's because it's a lake where there's no vegetation.
Yeah, I think.
That lake.
Yeah, it's water.
So you need vegetation to make this.
Yeah. We need vegetation. And finally, it's the unwrapped interferogram. So we can see actually here is the fringes, and yeah, and also here it shows the phase difference. Maybe we can switch to the this can see things clear.
You see some kind of pattern on the ocean, like the red.
Google will. Google will unwrap everything.
But that could be atmospheric, or
no. This is just Google likes to unwrap everything, so it just makes mistakes.
Yeah.
But these things, this is really so. The problem where that sharp corner was, you have to, when the unwrapper has to go all the way around.
Yeah.
So do you think that's correct? 20 radians. It could be 20 radians would be like 20 or 30 centimeters. It could be a lot more though.
Yeah. Fringes, I think there are 5 or 6.
Yeah. But at this point, you had a discontinuity. You couldn't measure the phase difference. So the unwrapper would have to go around here.
I see. Maybe it's better to unwrap unit by unit.
Yeah. So Eric's the unwrapper expert. But if you made, let's say you made many interferograms, all in sequence in time. The sum around, after you unwrap, the sum around every 3 should be 0.
Yeah.
And so you can identify an unwrapping error in that sum, and then come back and correct one of the interferograms. It's always 2 pi.
Yeah.
2 and pi. So you could uniquely unwrap all this with a big stack.
Yeah.
Did you say by some key of that?
0. So it's what Eric's been using to
Yeah, but this would be a great example. You wanted to switch this?
Yeah.
Do you have an HDMI?
Yeah.
Okay. Anybody else have anything they want to show before lunch shows up? Talk about. How do I get back to Zoom?
If you go back to the Zoom window,
Where's the Zoom?
there's an ape right down there, right on the bottom line, on the deck.
Oh, Zoom here.
Yeah, that's Zoom. If you click on that, maybe it's in the email sent by Melissa. There's a link. You can click on that and go back to the meeting.
It's this one here. Right here.
Yeah, just allow. Okay, there we go. Oh, that's my camera.
Is there anybody online that wants to share anything? You could put it in the folder and we could look at it. I have a speaker here where you can talk to us.
Yes, I already upload my slides. Have you seen it?
You uploaded your slides? Great. Let me see. Oh, yours is, okay, I'm sorry. How did I miss that? Let's see. Oh, we had this on another window already. It's on the Google Drive, okay. I'm all messed up. I got multiple windows going. Too many desktops. Escape. I'm really stuck here. Got like 3 things going. This is the one that's active, right? And why does it say your meeting should start in a few minutes? Click here to join the meeting. Allow. I think I'm in the meeting, right? Safari. New window. Google. So 2019 presentations. So these are the ones that have been. So is yours on in here?
Yes, I think the Lombok one.
Okay, let's do the remote one first. What's the name? Is it? I'm.
The InSAR Lombok 3M. That's mine.
Lombok. Oh, beautiful. Can you see the screen now?
Yes, I can see it clearly.
Okay. Come on. What's up? Lombok. I see that one there. Okay. And then how can we make it? I'm gonna bring this up in here so we can all hear.
Ready to pair. Go to the Bluetooth settings on your mobile device and choose Amazon Tap -0 KJ. Connected to Bluetooth.
There. Okay, we're connected. So we're gonna show your slides. Let me. How do I open them so we can get the full screen?
Okay. How to control it?
I can advance it. Present from the beginning?
Yeah.
Here? Okay, so we have slide number 1. And actually, I can't hear you through the speaker. Let me. Can you talk again?
Can you hear me now?
I want to try to make it a little bit louder. So let me come back here to the system preferences, sound, and we'll do the output through there, right? That'll work, right? Can you speak again?
Okay, can you hear me now?
Oh.
Hello.
Yes. But it's not coming through here. It says it is. Amazon tap, Bluetooth output. No? It should work, right? Can you just say hello again, please?
Hello. How about now?
It's
Hi.
good enough. Okay.
Okay.
We're going to try to get you to a speaker, but back here again. It's too many things. Okay.
Okay.
So, yeah, well, why don't you go ahead and I'll advance the slides for you.
Okay, sure. So I'm gonna start now. Okay, good morning, everyone. My name is Yuan. I am a PhD student in the Australian National University, and my previous work is all about creating some kinematic models by using GPS data and earthquake sleep vectors. But you guys must know, sometimes I will meet some situation that the GPS data is not enough. So at that time, I'm thinking about maybe InSAR is a very good tool to help me get out of this kind of situation. So this presentation will show some initial InSAR results for the 2008 Lombok region Indonesia earthquake. Well, actually, it's just two results. Lombok is definitely a tourist destination, and it's also a diving resort. So if you guys love diving or surfing, you must heard of this place. Yeah. And so next page, please.
I've been to Bali. I enjoyed that.
Okay. So as is known to us, the Indonesia is one of the most tectonic complicated regions in the world, which is characterized by the convergence between four different plates: the Australian plate, Philippine Sea plate, Pacific plate, and the Sunda block. And because this kind of convergence, this area is also highly seismically active. And we can notice from the seismic distribution map. Next page, please. Okay. Yeah. We can notice from the seismic distribution map here, there are over 8,000 earthquakes occurred in the Northeast Australian plate boundary zone between 1976 to 2018. And if we combine it with the population density map below, we can see the populated area is also the highly seismic area, and the Lombok is located in this region. Yes. Next, please. Yes, the geology of the Lombok Island is mostly made of volcano rocks due to the active Rinjani volcano. The volcano rises to 3,726 meters, making it the second highest volcano in Indonesia. Its latest eruption was during August 2016 that generated an ash plume that rose to an altitude of 9.8 kilometers. The bedrock is made of carbonate rocks, and we can see it towards the south and the southwest of this island. And before I move to the earthquake and the InSAR result, I want to talk a little bit about the tectonic background of Lombok and its surrounding. Just as I mentioned, the Lombok is located at the highly seismic area, and this is because of the convergence between the Australian plate and the Sunda block. The kinematic models here, which created by using GPS, by using the inversion of GPS and the earthquake sleep vectors, show that the alarm arc change in partitioning of plate convergence is caused by the anti-clockwise rotation of the Sunda band arc with respect to the Sunda block. The relative motion between the Australian plate and the Sunda block along the Java Church decreases from 70 millimeters per year at the Lombok Basin to the 33 millimeters per year at the longitude 122. Then along the Timor Trophy, it decreases from the 32 millimeters per year to about 1 millimeters per year. But in contrast, along the back arc, it increases from 6 millimeters per year to 33 millimeters per year at the Florius fault zone, which is really close, which is closely related to the earthquake I gonna mentioned. Okay, next, please. Okay. The 28th of July 2018 earthquake occurred on the Trust Fault, which is part of the Trust Fault, which is part of the Flores fault zone of eastern Indonesia. And the second stronger event occurred on August 5th, 2018, and possibly on an adjacent segment of the fault zone towards to the west. Okay, next, please. So these two tables here shows the data we used to derive earthquake focal mechanisms and the interferograms. The earthquake focal mechanisms are derived from the nodal planes data, which downloaded from the USGS, and then we use differential InSAR to capture the ground movements produced by these two earthquakes in the border area of Lombok. We construct interferograms by combining topographic information with SAR images by Sentinel-1B satellite before and after the earthquakes. So these two earthquakes actually happened between this time period. The details of the interferometric pairs for both interferograms are shown in this table here, in table 2 here. Yeah. Next, please. Yes. So this is the result of the raft interferogram, which shows the fringe pattern associated with the earthquakes, where each color circle demonstrates phase difference interpreted as ground deformation equal to 2.8 centimeters in the line of sight direction to the satellite. So by just look at this figure, we can find two apparent deformation area. One is located at the Bali Island, another one is the Lombok Island. But in this case, we just focus on the Lombok region. Yes. So next, please. So if we zoom in to the Lombok region, we can see the quality of the interferograms was not bad, but we can find noisy areas which are the results of low coherence. But if we combine this kind of low coherence areas with the vegetation distribution map, we can see that the reason of this kind of incoherence is mainly because these areas have dense vegetation cover. So the Sentinel satellites use the C band, which means this kind of band is hard to go through the tall trees or under their leaves. So I guess maybe use ALOS data. I can go better result because it's L band. So that's just my guess. And from this map, we can also see the deformation was localized at the northern part of the island, near to the 6.4 and 6.9 earthquakes epicenters. But if we calculate the fringes by manually, we can see it's around 10 fringes. Yeah, 10 fringes. But if we use the unwrapped displacement map, the things were going to be much more easier. Yeah, next, please. Yeah, so this is the unwrapped line of sight displacement result, and we can observe a preliminary maximum LOS displacement of 28 centimeters towards the satellite, and the minimum displacement minus 8.4 centimeters. 8.4 centimeters away from the interferogram, which correspond to the both events. And the focal mechanism of both events indicated almost east-west orientation of the ruptures and reserve kinematics. Yes, so yeah, that's all the stuff I found currently. In terms of the future plan, there are a lot of things we can do. First of all, I think is we can create a, oh sorry, I haven't finished. Sorry. The first thing we can do is to create elastic fault model at here, at the shown as the blue lines here. Yes, it's part of the Flores fault zone, and yeah, that's one thing we can do. The other thing I think we can do is to process an ascending data, sentinel data, and using the multi-looking angles to decompose the LOS, so we can got the EN and the vertical components, the results, the displacement. Yeah, that's my thoughts. Yeah, so yeah, that's
Great.
really I use, and thank you very much.
Thank you.
Yeah.
Have any questions? I have a question about, I know you haven't done the modeling yet, but
Yeah.
one thing I noticed in this slide that the fringes are very rapid on the north end of the area, and then they flatten out, and then they go back the other way. And so
Yeah,
sometimes
yes.
that's sort of the edge of the rupture, like the edge of the hinge zone.
Mm-hmm.
That might be where the rupture, I guess that would be up dip or down dip. I guess that's the up dip. I'm a little confused.
Actually, this kind of reverse, you mean the signal reverse at the end of the northern part?
Right at the end, yeah. Is that the edge of the fault?
Yes, actually, this kind of data the same data also being processed by USGS. They use the same data, but they use different software. They use the Sentinel-1 toolbox, and they also got this kind of what I call it, the signal.
Yeah, changes sign.
Yeah, change the sign. Yes, and they just mentioned some hypothesis, but there's no evidence to show it's just the guess. Their guess.
Yeah.
Yeah, and this sign reversal may indicate the active fault during the 5th August event may actually outcrop near the northwest coast of Lombok. That's their explanation.
Nice. So you're going to model this?
Yes, I want to create a model of this fault and say it's deep into north or deep into south, and try to and hope I can find more valuable results.
You know, we have the GMT developers here, and I wonder if they wanted to comment on your figures, which I think use a lot of GMT features.
Yeah, great. So,
Paul says they're very nice looking. Is this GMT5 or did you go to GMT6 now?
GMT5 SAR, yes.
Okay. Yeah, but I mean the figures you made.
Oh, the figures are created by GMT6.
GMT6, okay.
Yeah.
So they're happy that they see a new GMT6 user, the modern mode, right?
Yeah, the modern mode, yeah. Because I took the workshop with GMT6 2 days ago.
Oh, okay. I didn't
yeah.
know. Did you
so I
make
tried.
in the last couple of days, or did you make them a long time ago?
Last couple of days. This morning, I guess. This morning, actually.
What time is it there?
What time is there? I mean the morning is the afternoon, because the course every day the course start at 2 a.m. in Australia, 2 a.m. to 10 a.m. Yeah, this So I already confused about the time. I mean, because Australia is
the local time. But yeah. Okay. Is it breakfast time or dinner time?
breakfast time. Breakfast time. Australia is 17 hours late. Late before 70 hours before San Diego. Yeah.
No, I like these figures. They're very, yeah. And the results look great. So you just need to process some more examples, I think, and you'll have a good result here.
Yeah. And about the ALOS data is I want to ask if I use ALOS data, can I fix the incoherence part?
The ALOS will really help a lot. But the problem is you have to write a proposal to JAXA.
Oh, okay. So we don't have the access to ALOS.
Yeah. If you can find, you might be able to do it. There's an Asia data distribution center for ALOS, and maybe the Australians have a special deal for ALOS too. I don't know, but it would definitely help in the jungle there.
Yeah, great, thanks for the suggestion.
Any more questions? Or I guess we have one more presentation. Thank you for hanging in the middle of the night.
Yeah, thank you.
Two. I'm sorry. Okay. Good. Mouse back here. How do I get out of this without like killing it? There we go. Go back to Google Drive. Oh, good. Can we find yours here?
Yeah, it's here.
Oh, yeah.
Oh, and is there any? Sure. Was it Google Slides that couldn't go into full screen, or?
Let's see, it's present. It's this little button here, and then it's the second one down. Oh, yeah, the arrow. And then present from the beginning. Yeah.
Okay. Hi, my name's David de Guzman. I was going for my project. I was looking at areas of subsidence from oil extraction. So the study location, I was going to look at the area around Bakersfield. They have a lot of oil fields there. And if you don't know, Bakersfield is just, if you're not from the area, Bakersfield's just a little bit north of Los Angeles. So for the data, I looked at data from December 4th, 2017 to November 29th, 2018, using Sentinel-1 ascending. And this is just like a preview of like what those data sets look like. So when I ran them through InSAR, well, I tried to look at a small area and got my coordinates mixed up and ended up with this mess. And it ended up clipping a bunch of my data, so I had to go figure that out. But Eric was nice enough to help me and fix it up a bit. And so this is the results from that. There were a couple, the data was pretty messy. Apparently November and December is like not a great time to get data in that area with all the vegetation growing. But there were a couple areas I was interested in, specifically around here and up in this area here. So a little bit west of Bakersfield and a little bit northeast of there. And so this is what it looked like unwrapped. And so there were a couple areas of subsidence that And these are areas where there's active oil fields, so actively pulling up oil from the ground. And so just looking at it overlaid on Google Maps, yeah. But so, yeah.
That red area there, is that the oil field?
Yeah, so there's this one here. Yeah, so this whole hillsides are actually a bunch of oil fields. And then this area north of Bakersfield as well. So, yeah. But yeah, that's essentially what I got.
More questions or? Yeah, one more line.
Okay.
Oh, there's one more presentation online and also one more here. So do you plan to do more with this area?
Yeah, so I'm starting a master's program in the fall. Groundwater. From Topai? Okay. Yeah. Yeah. I know I'm also going to be looking at like where they're pumping groundwater, the wastewater back in, because in 2012, from the Bakersfield oil. Yeah. But since they're pumping water back in since 2014, they changed the laws. And they can't just have the wastewater in these open pools. So they're pumping it all back into the ground. And so we're going to see about that.
Thanks. You want to go now, and then we'll do the last one online. Do you have it in the Google Drive? Okay. Presentations. Go back. It's the last one down here. This one here, Mario. It's a PDF. I'm going to download it, and then we'll view it.
I think it's the right one. I think the most senior one before is mine.
Okay, well let's do the the remote one first then. Sorry.
Oh, sorry.
What's your? It's this one here.
Yes, this is mine. It takes a few minutes. So.
Okay, well let's do that, and then we'll go to Mario. So I'm gonna open it, and then presenter. Where is that? Can't remember how to do this. Open with Google Slides. Thanks for staying online so long today. And you're in, where are you located?
Sorry, I couldn't.
Where are you located?
Oh, I'm currently in Potsdam, Germany, and I'm but I'm a PhD student in Istanbul Technical University. So I'm currently visiting PhD students in Potsdam University and PhD candidates in Turkey.
Okay, so I think we're ready to go here. We have your slide.
Okay.
I just moved it. Okay, got it back. Oh. So everybody is here, and I've got the speaker up. So please go ahead.
My name is Mohammed Mohsen Yared. I'm presenting time series InSAR monitoring of land subsidence over north of Urmia Lake, Iran, using GMTSAR. This is page 2. Okay, this is Urmia Lake. It's one of the biggest hypersalinity lake in the world. And I was interested to land subsidence in north of this lake. And this lake is currently dried out, and it's very important for water resources engineers. So it's very, I mean, hot topic in water resources science. Would you please go next slide?
Next slide.
Yes. Yeah, so I processed 24 SLCs from descending track 79, mostly in 2017. And as you see, this is a plot of perpendicular baseline and temporal baselines. And I form about 53 interprograms. Would you please go next slide? Next slide. Okay. And I get a mean rate of deformation using the Scripps algorithm in GMTSAR, and this is mean deformation rate over northwest of O'Neill Lake, and this is the second burst of interprograms. As you see, we have relatively high rate of deformation in line of sight, about 15 centimeter per year or 10 centimeters. In the other side, we have some spot, which the main spot is Tabriz Basin. And it's good to mention that I have already processed this data with different algorithms. So I have already used the stamps. I used InSAR, and I also implemented a spots using inside the stamps. So I have the mean velocity from stamps PS algorithm and from SPOS algorithm, and also I correct atmospheric contribution using train. And still the InSAR time series is very noisy, so I decided to use GMTSAR and the SPOS algorithm inside GMTSAR to see how much it could correct the time series. And because I think the time series looks noisy, but the mean velocity looks very reasonable. So there is a kind of topographic correlation between the land subsidence and the mean velocity. And so, but I think it's because I checked a lot of interprogram, I can't be sure about this. This is related to mostly land subsidence, and it's not topographic correlated noise. And yeah, we have a volcano, as you see here, and close to the volcano, you see the land subsidence, which I think is controlled by faults around this basin. And also in this area, it's a very big fault. So it's a kind of structural fault, which I didn't plot it here. And it's there's interseismic noise also exists in the data, which you see. Yes, thank you. I'm interested to listen to your comments.
Okay, thanks. Any questions? So that area of land subsidence is, have you looked, is that where there's a lot of farming, or is that a city?
Yes, I think it's mostly related to anthropogenic activity and farming. I don't think it's related to municipal activity. It's too much for municipal activities to have such a land subsidence rate. 15 centimeters per year, I think it's very significant land subsidence.
Yeah, that's a very big number. Yeah. Any other questions? Or so did you use GMT5 or GMT6 modern mode, or these also look very nice figures?
Yeah, but it's from GMT5, but I trained by GMT6, but I'm not that much strong enough to use with GMT6 model. I have still some errors, but I have to learn more. I think it's very interesting.
Yeah, GMT6 might be a little easier to convert them. Any more questions? Okay, well, thanks for hanging in there on the line. Interesting results. So let's switch to Mario. Last but not least, presentations. I'm getting a hang of this now, how not to have to log in every time. Oops. No, I got to scroll down. There we go. It's a PDF, so I'm going to download it. Or did I already do that? Oh, it already opened. Oops. Okay, great.
Hi everyone, my name is Mario Mendoza. I come Peru, and I work in the Institute Geographic National, and I work with GPAs. I manage the net of GPAs of all Peru. Yeah, and this is my presentation. Sorry for my bad English, but I will going to try. Okay. Don't know what. Okay. This is my steps for processing in GMTSAR. What you need to work. What is it? Okay. What do you need to process this? First is you need to imagine of different days. Okay, of same place, Sentinel or another imagine. Okay, this is the imagine. The first day and the second day, and we need to visit the website of Copernico for download these files. This is the first file and second file. Yeah, and then you need to ephemeris according the days of the images. Okay, this is the first ephemeris, and the second ephemeris. This is the date. Okay, I use it this is the first day and this day, the second day. Okay, and then we need the DEM. Okay, the digital elevation model. You need to visit the website GMTSAR for download this information, this data. Okay, when you have all information, okay. Don't know what. Okay. For see the information, you can see the imaging in the Google Earth. This is the digital elevation model, and this is the first day of imaging. Okay, and this is the second day. Okay. Well, and then this is the all data. Okay, and then what you need to group is you need to aggregate the information. Okay, you need the directory route in minus and directory topo and a file config, okay, point tops and txt, and then you have to put the information in this directory, okay, and this is these two and this directory top, and then you need to you must be here, and then you need to execute this command line, okay? When this is the command for process in GMTSAR. P2P, okay, and then you need to put the name of files in this order, okay? The first day, the ephemeris, and then the second day, the last one, the second ephemeris, and then put this. But in my case, I didn't work in my GMTSAR in a computer because I don't know. I tried it a lot yesterday until the night, but I tried it. Yeah, this is the problem. But I going to try again. But now no, the other day. Okay, this is the problem. What happened? Okay. Well, but I need to process in GMTSAR in my country. I will going to try and correction this problem. Okay, because I need the information. Because I need to put the information of cell processing in my map of country, or to see the displacement, no? Okay, and then compare with the point or displacement of GPAs. Okay, this is, for example, each point is a reference GPAs, station GPAs. Okay, these are rows is the displacement of the before and after of the seismic or airport, okay, of dates of 26 May 26 in this year. The had one seismic 8 magnitude.
That's the deep one. It's deep.
What?
It's very deep. Profundo.
It was 40 kilometers in this place. Okay, and this station, the distance is 100 kilometers, and this had the maximum displacement. This arrow gives your direction, and your magnitude is 4 centimeters. Okay.
40?
Yeah, no, 4.
4 centimeters.
4 centimeters, yeah. And this station is affected by this focus. Here, up, no problem. Yeah. Okay. And this is the computation for the seismic. And I need to analyze with data processing of SAR for to see how was the deformation around in all country, okay, and compare and correct and good correlation. Yeah? This is other case. I work with the gamut. I use gamut for processing each day or all weeks or all years the data of all stations. And it is an example, okay, for an station. This is computation, okay, for 1 year. For example, it's very interesting. This in the first months, weeks. This is the computation, and then sleep. Okay, a step or a sleep. What?
Is that an earthquake or no? It's slow.
No. It's for the, I don't know, for the displacement of the plate.
Yeah.
Yeah, I don't know. It's good for investigation. What?
Whereabouts is that station?
This station?
Yeah. Arrow.
Okay, this is I believe is it for here? Yeah, it's here. No, I can't see. We can't see. It's it for here. Yeah.
Do you know if the end of station is supposed to be at the
I don't know. Yeah.
Do you know if the end of the station is close to where the magnitude 8 get explosive as well?
Same this? Yeah, but I not put in the slides. Yeah, but I have for all stations for each day. Okay. And okay. Bueno, this is my work. This is my country. This is all stations. We have 69 stations here. All connected, good. Okay. Well, it's very important to me for my country work with GMTSAR for make this analysis. Okay. Well, I first what I'm going to do in my country is to make GMTSAR for work. Then I'm planning to look for SAR imaging from my region after and before the May 26 airport, and be able to analyze it variation and then validate it by using GPS observation. Okay. Thanks GMT team and thanks GMTSAR team. Thanks. Thank you. Okay.
Oh yeah, everybody should be picking up their certificates when they leave. Over here. Help people. Thank you. So let me go back on your slides here.
So this station went 40 millimeters in how many days? Maybe. How long was this time? 1 month?
No, it's 0
It's
to
all- Maybe
350 is the all days of the
that's
year.
1 year.
Yeah.
So this is a month or a few weeks. A few weeks.
Approximately, yeah.
That's a big signal, yeah. And there's another one here.
Yeah.
Huh. And that would be right here.
What's super interesting is you have like the down the so you see slow stuff on the station on the right hand side. Like you're saying it's slow stuff and the down the extinct is like
Yeah.
but then you also generate on the tip you also generate the main like trust with
Yeah.
saying that you can generate these slow stuff.
USB is the same
122. But it's still a lot of surface deformation. That's 4 centimeters. Wow. So when you tried to make the interferogram, it didn't work. We could try it again at lunchtime. If we can get it to work. Yeah, that'd be really interesting. And it would be interesting to look at this interferogram. That one.
But that is the information of the year 218. It is an example.
That's okay.
But the other is for this year in May
Yeah.
26 earthwork.
But it doesn't matter. We have data back. The data goes back till 2015. So you could look at this one and that one.
So in the middle, time series is positive going east.
That's the east. That's the east. I guess it's going, yeah,
I think it's positive. Yeah.
going that way. So the,
If it's source event,
yeah, it should go the other way.
it's not
Wow.
in the wrong direction because source event probably should go toward the ocean. The direction is opposite.
No, but this is the slow slope.
Oh, it's slow slope. Oh, okay. Yeah, that's what it said, yeah.
The normal fall?
Yeah, it's deep. I mean, it says flat the plates are breaking. So you might expect,
Okay, well, thank everyone for all those presentations are great. We're gonna put them online if it's okay on the Untitled site. As a record that you guys all did some work and you have to pick up your certificates. And there's lunch here, so we can do more over lunch. Okay.
Yeah, we get them like 3 hours.
On the Google Drive. We gotta get that interferogram to work.
Yeah. So, I didn't catch up. Just the one that you see these kind of things, so how do you tell stories early? That one, or you from your mind. So that's the in the middle one. That's the
Thanks everybody for hanging in there. We're gonna shut down, but I enjoyed your presentations and discussions. Thanks again.
Thank you.